I welcome you all to this MOOC course on stochastic processing, second session. So in the previous session, the introduction of sample space, random variables, properties of cumulative distribution function, properties of probability density function, and some important PDFs and CDFs have been discussed in the previous session. Now, in this session, the operations on single random variables will be discussed. So, before proceeding to the discussion, I want to give an example of a digital communication system example. So, if I want to transmit logic 0 and logic 1, so a typical example I'm considering here, 0 is transmitting by means of 0 volts. Logic 1 is transmitting by means of plus 5 volts. At the receiver side, a decision device will be there if the incoming voltage is greater than, say, threshold value of 2.5 volts. The input voltage, the incoming voltage is greater than 2.5 volts. Decision will be taken in favor of logic 1. If the incoming voltage is less than 2.5 volts, decision will be taken in favor of logic 0. Suppose a noise is added during the transmission. It may be wired or wireless communication. If a noise is added, suppose logic 0 has been transmitted at the transmitter side, 0 volts, and noise is added, say, above 2.5 volts. So 0 is transmitted at the receiver side. The incoming voltage is greater than 2.5 volts. So decision will be taken in the favor of logic 1. So here the probability comes into picture that what is the probability that noise voltage lies greater than 2.5 volts, or what is the probability that getting noise voltage greater than 2.5 volts. So this is how the scenario of noise will comes into picture in digital communication system. And the statistical parameters. See, the moment random, no mathematical description has been there previously. If you say a deterministic signal, you can give a beautiful equation to each signal. Now it is a random signal. So in previous class, we discussed that the characterization of random signals by means of cumulative distribution function and probability density function. In continuation to that, some statistical averages. These statistical averages are generally called as ensemble averages. Will be calculated on the random variables, and it's purely depends on its probability density function. So see here, expectation operator. Expectation operator, generally it is called ensemble average. So x is a random variable. Remember that random variable is always function of sample space. So x bar is equal to, that is generally we call this x bar is the mean of the random variable x, represented as expectation of x. See, the formula is always filled with fx of x, the probability density function. In the brackets of expectation operator, we have x. So here a small x will be considered. So x bar is equal to expectation of x is equal to minus infinity to plus infinity x fx of x dx. Whatever the thing is there in the brackets of expectation operator will be copied down here in the integration, multiplication with its probability density function. If x is a discrete random variable, x bar is equal to E of x is equal to, the integration will become now summation. Summation from I is equal to 0 to capital N, xi p of xi. P of xi is called the probability mass function or probability density function. Similarly, whatever there in the brackets, so expectation of g of x is equal to minus infinity to plus infinity, g of x, fx of x, dx. Whatever the thing there in the brackets of expectation operator, copied down into the integration, multiplication with its probability density function. This is ensemble average, the operations on single random variable, calculation of statistical parameters to evaluate the random variable behavior. So in operations on single random variable, the first point to be discussed here is movements about origin. So in place of the last one, expectation of gx, this formula, if g of x is equal to capital X power n and n is varying from 0, it's always an integer value, 0, 1, 2 and so on up to infinity. And it is called movements about origin. Why? Because x power n can be written as x minus 0 whole power n. So next thing to be discussed is movements about mean, where we can write it as capital X minus x bar whole power n, that are called movements about mean or movements about central movements. So the notation m suffix n, m is representing the movements about origin. The suffix n indicating the order of the suffix n indicating the order of the movement is equal to minus infinity to plus infinity. The brackets, it is x power n. So small x power n fx of x dx. So we can calculate all the movements, zeroth order movement, first order movement, second order movement, and so on. So first substituting n is equal to 0 equal to e expectation of x power 0 is equal to minus infinity to plus infinity x power 0 multiplication with the pdf dx. X power 0 is 1. So the equation becomes now minus infinity to plus infinity fx of x dx. This is the area under the probability density function. Seen in the previous session, the area under the probability density function is always unity. So the answer is 1. That is 0th order movement about origin is 1. Second one is m suffix 1, first order movement. First order movement is equal to expectation of x power n is equal to minus infinity to plus infinity x of 0 fx of x dx. This is the previous slide, we have seen this. So it is x bar, mean of the random variable capital X. M1 is the first order movement about origin, is called x bar, mean. Likewise, you can extend M2, M3 and so on up to Mn. Generally, M2 is equal to expectation of capital X square is equal to minus infinity to plus infinity x square fx of x dx. Generally, it is represented as x square bar. That is ensemble average. Next one. Movements about mean are central movements. Movement about mean are central movement. So in place of g of x, x minus x bar whole power n. So Movements about origin in the place of x bar will have 0. Here, g of x is equal to capital X minus x bar whole power n. And n is an always integer value varying from 0, 1, 2, and so on up to infinity. The symbolic notation represented for central movements is mu suffix n. Again, similar discussion. Mu is movement about mean or central movement of order small n. So, which is equal to expectation of x minus x bar whole power n is equal to minus infinity to plus infinity x minus x bar whole power n fx of x dx. Think there in the brackets of expectation operator copied down here. So mu0, mu1, mu2, likewise you can calculate. So first parameter is again mu0. This is 0th order central movement. So is equal to expectation of x minus x bar whole power 0 is equal to minus infinity to plus infinity x minus x bar whole power 0 fx of x dx. So this x minus x bar whole power 0 value will becomes 1. The leftover component is only the probability density function. So minus infinity to plus infinity fx of x dx is equal to 1. It is the area under the probability density function. Next one is the first order central movement mu1 is equal to expectation of x minus x bar whole power 1. So x minus x bar expansion e of x minus e of x bar. Remember that for a constant value, expectation of constant value is equal to constant. Expectation of constant value is always equal to constant. So E of x is equal to x bar. E of x bar is equal to x bar. X bar minus x bar is 0. X bar minus x bar is 0. So first order central movement is 0. 0th order central movement is 1. Then second order central movement is generally called as a variance of the random variable x. Variance of the random variable x. While discussing in communication system also, it will be given in the problem that noise having mean and variance, some values, it will be discussed. So variance, second order central movement, generally it is denoted as mu2 is equal to sigma x square. Sigma x is called standard deviation. Sigma x square is called the variance of the random variable. So sigma x is standard deviation. So some mathematical derivation here, mu2 is equal to sigma x square is equal to expectation of x minus x bar whole square. So a minus b whole square expansion in the inner brackets of expectation operator, capital X square plus x bar square minus 2x x bar. And expectation operator can be separated like this. So first parameter is x square, expectation of x square. Second parameter is x bar. You can write x bar, but I have written here e of x whole square minus 2x bar is constant, x bar is written as e of x. So the leftover parameter is e of x. So e of x square, e of x whole square minus 2 e of x whole square. So we can write this finally. Mu2 is a sigma x square is the second order central movement, also called the variance, is equal to expectation of x square minus expectation of x whole square. Be specific, we can write it as m2 minus m1 whole square. M2 is second order movement about origin. M1 is the first order movement about origin. So the variance and mean are the important parameters generally discussed in communication system, while the signal is added to the noise. Noise with mean 0 and variance 1 is a typical sentence generally used in communication problems. So the central movements generally used to test the randomness of signal, randomness present in the signal is by means of skewness and kurtosis. So third order central movement is generally called as coefficient of skewness. So sorry, third order central movement is used in measurement of coefficient of skewness. So third order central movement is denoted as mu3 is equal to expectation of x minus x bar whole power 3 is equal to whatever the thing is there in the brackets, copy down here, minus infinity to plus infinity, x minus x bar whole power 3 fx of x dx. So the normalized third order central movement will be generally called as a coefficient of skewness. It is mu3 by sigma x power 3. And normalized fourth order central movement is called kurtosis. That is mu4 by sigma x power 4. Generally, these two parameters are used to test the randomness of the signal. In specific, in my research work, in good number of papers, I have used the skewness and kurtosis for measurement of random noise. So the next parameter is generally called as movement generating functions. So from those functions, we can generate the movements about origin, movements generation function. So in this, the first one is characteristic function. It is characteristic function denoted as phi x of omega is equal to expectation of e power j omega x. So expectation of e power j omega x. So substituting in the formula, phi x of omega is equal to expectation of e power j omega x is equal to minus infinity to plus infinity e power j omega x multiplied by pdf dx. But this formula is looking like a Fourier transform formula. But in Fourier transform, we'll have e power minus j omega t. But here we have e power plus j omega x. Likewise, if you write inverse Fourier transform formula, the PDF can be extracted from the characteristic function. This fx of x is equal to minus infinity to plus infinity phi x of omega e power minus j omega x d omega. And the thing here is that the point of discussion here is that movements can be generated from the characteristic function. That is, the formula is m suffix n is equal to minus j whole power n d derivative of power of n phi x of omega by d omega n at omega is equal to 0. So movements can be generated from the characteristic function. So if you want the first order movement, minus j whole power n minus j whole power 1 d phi x of omega by d omega, substitute omega is equal to 0 after doing the differentiation and multiply it with minus j whole power n. So likewise, you can get all the moments of nth order from the characteristic function doing nth differentiation and substituting omega is equal to 0. And this is the simple proven thing, that is magnitude of phi x of omega is always less than or equal to phi x of 0. So in this equation, if you substitute omega is equal to 0, the equation becomes minus infinity to plus infinity fx of x e power omega. In place of omega, we are substituting 0. E power 0 is 1. The leftover parameter here is minus infinity to plus infinity fx of x dx is equal to 1. That is it is area under the probability density function. So phi x of 0 is 1, and the maximum value of characteristic function occurs at origin. For all other values of omega, its value is less than maximum value. Likewise, one more parameter is there, moment generating function. The formula looks very similar to the characteristic function. The J operator has been removed from the previous formula, that is characteristic function. So it is represented as capital Mx of V is equal to expectation of e power Vx. So likewise, expansion of the formula, Mx of V is equal to expectation of e power Vx is equal to minus infinity to plus infinity fx of x e power Vx dx. Similar to the previous characteristic function, this moment generating function, the name implies the movements can be generated from this moment generating function. So which are m suffix n is equal to d power n mx of v by dv power n, and substitute v is equal to 0, similar to the characteristic function discussion. If you want the first order movement about origin, m1 is equal to dmx of v by dv. After performing the differentiation with reference to v, substitute v is equal to 0, gives the mean of the r first order movement about origin of the random variable x of t. Likewise, m1, m2, m3 and so on up to mn can be generated from the moment generating function. So this comes to the end of lecture 2 of 4-week MOOC course on stochastic processing. And in the next session, we'll discuss the problems on the PDF, CDF and operations on single random variable. Thank you.